Welcome to this video introduction to the diode. The purpose of this video is to introduce the diode as an element in circuit analysis and help you understand how it works and how to do a simple analysis of it. So the symbol that we have here in the upper left represents a diode. It's represented by a triangle, which I'll color in just to make sure it's clear, and a vertical bar. About half the time in schematics you'll see the diode triangle open, and the other half you'll see it colored in. I've also labeled the voltage across the diode and the current going through the diode, so we'll talk about these in just a minute. Diodes, anymore at least, are almost always solid-state devices, so they're made out of a semiconducting material. Most of the diodes made today are made out of silicon, and the silicon has impurities diffused into it so that you get certain behavior. And we'll talk about that in just a minute. The equation that we have here is the Shockley diode model, and this model is derived from the physics associated with the diode structure in the silicon or other semiconductor. You'll notice that we have the current as a function of I sub s, e to the v over nvt minus 1. And to give you a feeling for some typical values of these constants, I sub s is, for a silicon diode, typically about 10 to the minus 12 amps. And again, for a silicon diode, N over Vt is typically somewhere between 0.25 volts to 0.05 volts. Okay, so the diode has a fairly interesting VI characteristic, which we can plot using this equation and these typical values. When V is positive, then I get something that's very nearly, the current's very nearly zero, starts to go up exponentially, and then at some threshold voltage actually takes off and becomes almost vertical. And this threshold voltage is typically called V sub D. It's a forward bias voltage of the diode. And again, for a silicon diode, this V sub D is typically about 0.7 volts. For a light emitting diode, this V sub D may be 2 volts or even 3 volts. So the materials out of which you construct your diode affect V sub D significantly. Okay. Now, this curve where the voltage, or for small values of voltage, you get almost no current, and then all of a sudden you get a large current, is an extremely useful thing, and we'll talk about this in more detail in just a minute. A diode that has a positive voltage and hence a positive current, so a diode out in this area of the VI curve is called a forward biased diode. Okay, now if the voltage is negative, you can see from this expression, if this voltage is negative, then the diode current is also negative, but it's very, very small. So for negative voltages, you get a small current. This current's often called a leakage voltage, until you get out to some point out here, where this is called V B sub t. So this is actually what they call a breakdown threshold. And at this point, the VI curve goes like this. And what basically happens is, well, let me put in some terminology first. This region between here and the origin, this is called reverse biased. And the idea is that the voltage is negative, so the current's very small. And once you get out past this threshold VBT, so you're in this region, this is called breakdown. And basically what happens is when the voltage across the diode becomes negative enough, then the diode actually breaks down and allows current to flow through it in the opposite direction to which current normally flows. In most diodes, if you get breakdown, it's catastrophic in the sense that you'll destroy the diode. There is a specific type of diode called a Zener diode that is designed to have a very specific reverse or breakdown threshold voltage, and is designed to operate in the breakdown region without any damage. And so it turns out that you can use Zener diodes as fairly accurate voltage references when you need to make sure that your voltage across a certain point, typically in a power supply, is equal to some value. Okay, so this is the VI curve, and again, the most useful bits of it are these parts up here, and then this part here. Again, except for Zener diodes, you really don't want to drive your diodes into breakdown because that's not a good thing. So what I'd like to do now is spend a few minutes talking about how we can approximate this VI curve, because it turns out that most of the time you don't want to deal with the Shockley diode equation directly. The only time where this equation turns out to be an important model is when you are using a diode to build, say, a logarithmic or an exponential amplifier with, say, an op-amp. And that's really beyond the scope of what we're talking about today. So you typically don't want to use the Shockley diode equation directly. And what we do is we come up with a couple of approximations, depending on what we're looking at, for the VI curve for the diode. So let's make the Shockley diode equation go away, because we've outgrown it. And let's look then at these approximations that we can develop for the VI curves of the diode. So one approximation that we use, and this is typically what we use when we're dealing with diodes in high power applications, we can take the line in the forward bias part and represent it by just a dashed line that's tangent to this forward biased curve at some point. So basically we have something that looks like this, where again this is the VD threshold, and then for all the other voltages below VD, we just have the current equal to 0. So that's basically representing this part of the curve. And the slope here is a value 1 over R sub D, and R sub D is essentially the resistance of the diode at the operating point. So, for example, if you are working in a high power application where you're running, say, tens of amps or maybe even hundreds of amps through this diode, maybe a power diode, so that your point is up quite high on the I curve, then you make your line, this slanted line here, you make that tangent with the VI curve at this point, and that gives you a good approximation for the resistance of your diode at that operating point. So again, this is typically used for high power applications. Now, when you have lower current, a very useful approximation is this. And we'll draw this in red. Rather than drawing a line with some slope 1 over RD, we'll basically draw just a vertical line. And then we have a horizontal line for voltages that are lower than V sub D. And so the idea here is that this is a diode. This is typically useful for relatively small currents. And the idea here is that when the diode is forward biased, I have essentially, I can represent the diode as just being a voltage source of value V sub D. Okay. When the diode is reversed biased, so basically this part of the model applies over here. When the diode is reversed biased, then the diode just looks like an open circuit. Now this is again useful. Most of the time you'll see this used when V sub D is a significant fraction of the maximum voltages that you're going to use. When the maximum voltages that you're going to use are much larger than V sub D, quite often you can ignore that V sub D and come up with an even simpler VI curve, which looks like this. You assume that V sub D is small. In fact, it's small enough to be insignificant. So your VI curve just follows the axes here. Okay. And so in this case, when the diode is forward biased, that is when the voltage is such that you have the diode conducting current, then your diode is just representing a short circuit because the voltage is always zero and you can run any amount of current through it that you want to. And when the diode is reversed biased, out in this region, your diode is modeled by an open circuit because no matter what the negative voltage is out here, the current is always zero. Okay, so these are the three models that you typically use. Again, for high power applications, you typically use this model over here where you are representing the resistance of the diode. For lower power applications, where the voltage, the maximum voltage you're dealing with is not that large relative to V sub D, you use this model. And when you can neglect the fact that V sub D is non-zero in real diodes, you can use this model. This model, the last one that we did, is by far the simplest model to use. But again, it may or may not be accurate enough for what you need to do. So that will conclude this video.